Good day everyone, especially to my STEM students. It's me once again, your Sir Jomari Silibio, and today we will be dealing with another topic, still under measurement, but this time we will try to focus on errors in measurement. So I hope that you will bear with me as we discuss this new topic, which is focused on errors and in measurement. Okay. So still we are dealing with general physics. Okay, and still we are trying to consider the most essential learning competency that serves as our guide in dealing with these topics. Okay, so still we work with the same content standard as what we have before, but this time we'll now focus on the effect of instrument on measurement, uncertainties and deviations in measurement, as well as sources and types of errors while conducting a measurement. Okay, so as what you can see, we have to be guided by this most essential learning competency. So these are the competencies that we will be dealing with. This time we'll try to differentiate accuracy from precision. So later on, at the end of this presentation, I hope that it's possible for you now to differentiate accuracy from precision. Okay, next, it's expected also that by the end of this, you will be able to differentiate random error from systematic error. Okay, so and last one, we have to deal with the estimate errors from multiple measurements of physical quantity using variance. Okay, so these are the topic that we'll be dealing with as we go on with this content. Okay, so once again, we're still on measurement, but this time focused on errors and propagation of errors in measurement. Okay, so errors in measurement. So we are all aware, and we have discussed last time, measurement. So measurement is the basis of most scientific study. Okay, so most scientific laws and scientific breakthrough are largely based on measurement. Okay, so measurement plays a very important role, and it's one of the very important processes that are considered in physics. All measurements are, however, approximate values, and they are not considered to be the true value. So when we are conducting measurement, what we can obtain is not actually the true value. No, however, we can do what we call approximation. It's probably because of some limitations of our measuring instruments. Like, for example, in the case of 1 meter, so what we can infer probably are just measurement up to millimeter. It's impossible for us to accurately describe the measurement of length in terms of micrometer or let's say nanometer. They are very small, so it's beyond the ability of some measuring instrument like a meter stick. Okay, so there are limitations. There are also limitations as far as the measuring environment is concerned, and also in the process of measurement, and there are instances wherein human itself, while performing measurement, commits certain error. Okay, so in measurement, our goal is indeed to minimize, reduce, or limit the possible error that we could possibly incur while doing what we call measurement. So we try to reduce them so that our measurement will become meaningful, and the value obtained will be very close to what we call true value. So there are two general categories as far as errors is concerned. So the first one, the errors could be categorized as either systematic error or a random error. So those are the two general categories of errors in measurement. Okay, so the next, we will deal with accuracy and precision. So those errors that we have mentioned earlier may affect what we call accuracy and precision of our measurements. So one of the primary goal of measurement is to establish what we call accuracy and precision. Okay, so when we say accuracy, it refers to how close the measurement with respect to the true value. So a true value of a quantity is a measurement when we try to reduce all errors as much as possible. We try to account them, and we try to do some means to minimize those errors. Okay. So precision, on the other hand, has something to do with the ability of an instrument to measure values with consistent result. Okay, so if we consistently obtain a certain measurement with consistency, then we can say that our measurement is precise. Okay, so for example, um, on the first measurement, we were able to obtain 6.5 meters. By the second measurement, we obtained 6.6 meters. Then by the third, 6.5 again. So it simply implied that our measurement is precise because it is producing what we call consistent result. Okay, a precise measurement may not always be accurate. However, in contrast, accurate measurement is considered to be a precise one. Okay, so that's the difference. As what you can see now in this case, when we say accurate measurement, it always hits the what we call the target. You are having an what we call accurate measurement. Okay, another case is, say for example, you were able to have consistent result. Although the result is consistent, it's said to be precise. However, it may not be accurate. If you were able to get accurate results in measurement, then it's always precise because it always is closer to what we call the true value. Okay, so these are the ideas when we say accuracy and precision. So it could be precise, but it might not be accurate. However, accurate measurement will always be precise, is a precise one. Okay, so systematic errors and random errors. So when we say systematic error, a systematic error results due to faulty measurement practices. So probably there are errors as far as our practice is concerned. So when we say systematic error, it is something to do with the errors in the system. Something is wrong with the system. Something is wrong with the procedure or the way we implement the process of measurement. Okay, so there are probably sources of this error. The first one is the faulty instrument. So probably we can attribute this to the poor design of the instrument. Some instruments may not be suited probably to the desired measurement that we wish to attain. So other instruments may have faulty design, or other instruments may be undurable, or they lack durability. So they easily wear down when we use them at certain temperature. They are affected, no, and the results are not accurate. Or somewhat, some instruments that we are using are inefficient. Sometimes they fluctuate, and they didn't give such what we call efficient result. Okay, so the next thing is the faulty measuring process. Like say for example, we skipped certain procedure, or we were not able to follow the proper procedure. That's the case wherein we wish to replicate some measurements or experiments done by other scientists. So sometimes we missed something, and the result is of course error. So those are attributed to what we call systematic error. Other sources may probably be attributed to the following. So we have personal bias. Okay, so when we say personal bias, it's something to do with our habits probably. Sometimes we are lazy to wait for the result, or we are lazy to do the best measurement practices. Sometimes we are not in the mood, okay, or probably you're not in the mood of doing something, so it may also affect your measurement. Other specific example is attributed to what they call parallax error, wherein it's something to do with where you position yourself in performing measurement, because at certain angle it seems that your reading will be affected. So for example, you are standing at the side and is trying to read the measurement, it's affecting the result of the measurement. Okay, so these are some possible sources of what we call systematic error. Okay, another type of error is what they call random error or random errors. Okay, so random errors are results from unidentified or unknown conditions in an experimental setup. So for example, we are conducting an experiment, and in the process there are some unknown conditions that resulted to the error, and this is attributed to what we call random error. Okay, some of the measured values are greater than the true value, some are less than the true value, so probably we can attribute that to the random error. So these errors are sometimes referred to as accidental errors. So the errors introduced are sometimes attributed to the fluctuation, for example, in some physical factors like air temperature. All of a sudden, the temperature becomes humid. Or say, for example, the pressure becomes stronger, there's strong wind, or probably there is a fluctuation of voltage if we are using a device that is plugged into electricity. So there is what we call voltage fluctuation, or instability of some mechanical or electrical parts. Okay, so these are some errors that could probably affect the result of our study. So we call them as random errors. Okay. So it is possible to minimize, however, this random error. So it could be done by, of course, repeating measurements, and of course by applying the statistical technique, so that at least we can get closer to the true value if we're able to minimize or to repeat this experiment. Another distinguishing aspect of random error is that it's not biased. So meaning it's not influenced by personal factor or personal biases. Okay. So one of the approaches in measurement is the use of what we call the least count error. Okay, so this is one of the method that is employed to at least minimize the error. So they use what we call the least count error measurement. So the least count error results due to inadequacy of resolution of instrument, and we try to consider what we call the least count of a measuring device. So we consider this what we call least count. So the least count of a device, what is this? It has something to do with the smallest division on the scale that our instrument is capable of reading. Say for example, if you have a meter stick, then it's capable of measuring centimeters, or it's also possible of to measure millimeter. However, beyond that, it's somewhat inaccurate to conduct some estimation, because it seems that the instrument is no longer capable of performing such. So the least count for a meter, for example, is millimeter. It is the smallest division in which the instrument is probably capable of performing a particular measurement. Okay, so the generally accepted level. So when we read, for example, the reading using those instruments, we try to consider what we call the smallest division. Okay, so and we usually consider the half of the least count. Okay, so let's try to consider some examples. Okay, say for example, this x, this is the measurement of length. The measurement is 0.599. This is the smallest possible measurement, because it's in terms of meter, and the smallest division could be in thousandths, milli, tens, hundreds, thousandths. and because of that we divide that by 2, so we consider the half of the least count, then half of this will be this one, 0.005. Therefore, if we measure this value, we obtain that, and we would like to express or report that in terms of meter, then it should be reported as 0.599 plus or minus, this is the uncertainty, it's the error in possible error, plus or minus this one, half of the least count. Okay, so this is how we report the data that we obtained in terms of meter. On the other hand, notice that if we wish to report in centimeter, for example, you measured and you wish to report the measurement in centimeter. Okay, so of course, for example, you obtained 59.9 centimeters. Okay, you will notice that you consider the half of the least count. For example, because it's capable of performing up to this point. Okay, so half of that is 0.05. Okay, so because of that, we move one decimal place. So the report should be 59.9 plus or minus 0.05. Look at how it moved one decimal place. And half of that is the half of the least count, is the accepted way of expressing this measurement. Okay, so this is the idea. Okay. If we report, on the other hand, the measurement in millimeters, so for example, what you obtained is 599 millimeter. Okay, it should be reported as 599. However, you will notice that half of the least count from here could be, half of that is 0.5. So it should be reported as 599 plus or minus 0.5 mm. Okay, so that's how we consider. We consider the least or the last smallest possible or the least count in which it's capable of measuring, and then we take half of that, and that's it. Okay, that's how we obtain it. So once again, we try to consider this. This is in terms of meter, and we get the half of the least count, and we have it as plus or minus to account for its error in measurement. And the same is true with here, so it's capable up to this point. Therefore, half of this will be, half of the least count will be 0.05, and that's how we report in terms of meter. So that's again a recap of how we consider the least count in determining or in reporting measurement. Notice that the half of the last count is around 5 or 0.5. And the decimal place is considered to account the errors in the measurement. So that's what we have noticed. Okay, repeated measurement could be employed again to minimize the error in our measurement. The averaging of the repeated measurement serves as the ideal estimate of the true value. So oftentimes we get the average, and the average of our measurement is somewhat considered to be the true value, because it seems that the repeated measurement produces a value that is closer to the true value, and oftentimes as practice, that's what is being considered as the true value. So the average or the mean of the measurements is distributed contextually as the true value of the quantity being measured. Okay, so that's once again the common practice that we are trying to consider. Now we will try to work with errors. So there are basically three related approaches which involves measurement of the absolute error, the relative error, and the percentage error. So these are some errors that are being considered, no? So the absolute, the relative, and the percentage error. Okay, when we talk about absolute error, this is the magnitude of error, and it's determined by considering the difference between the obtained measurement and the mean value. So we have the absolute error, or the change or the deviation from the mean. Okay, so the difference, the absolute value, the deviation from the mean, is what we call the absolute error. So it's just simply the difference between the mean and the measurement. Okay, so the absolute value is the what we call absolute error. Okay, so we have here the label. This is the mean minus the measurement. Okay, so we can obtain the absolute error. This is sometimes also referred to as the deviation from the mean. So the absolute value is what we call the absolute error. So consider the example that we have. So supposing we have 5 measurements. We're trying to measure the length. Okay, so we have 5 trials, and these are the measurements that we obtained. So you will notice that we try to consider the average to be our true value. So to do that, we simply have to add the individual measurements, obtain the total, and divide that with the number of trials, and in which case we're able to obtain the average, in which we could consider this as our true mean. Okay, the average is 1.599. The next step is to determine the deviation from the mean. Okay, so to determine that, we simply subtract the measurement to the average or the mean. So in this case, we have the value, which is 1.599. The measurement minus the average, it's 0. Okay, so the measurement minus the average, it's 0.001. Okay, so we have the same value. Okay, next one we have negative. Okay, and for the 5th measurement we have 0 deviation from the mean. Okay, so and then we try to consider the absolute value or the absolute error. Okay, so by applying the absolute value, then we ignore the negative sign and eventually sum it up to have a what we call the total of 0.003, and then we take the average, and this is the average that we're able to obtain by considering this example. Okay, so as what you can see, we have now the mean of the measurement and the average mean absolute error. Okay, so we have this one. Okay, next. Okay, once again, the absolute value is the what we call the absolute error. Okay, for every measurement, and then eventually there we were able to determine the mean absolute error. Okay, so the measurement could therefore be reported as this is the average that we've obtained and the what we call the mean absolute error. Okay, so or the mean absolute deviation, where 0.006 is the mean absolute deviation in this case. Okay, so that's how we report the measurement that we have. Okay, so we can also report range of error as the ratio of the mean absolute error. This is the mean absolute error that we obtained divided by the mean of our measurement. Okay, or the mean value of the quantity. So this ratio, if we take this ratio, is what we call the relative error, and others may consider this as the fractional error. So this is the mathematical expression of the fractional error, wherein once again we just simply divide the mean absolute error to the mean of the quantity obtained. Okay, using our previous example, then this is the setup, or this is how we compute for a fractional error, and we were able to obtain 0.0004. Okay, this ratio implies that 0.004 is the amount of error which is possible for every meter of length measured. Hence, if there are 1.599 meters of total length, then the amount of error possible is equal to this. Okay. Okay, the next topic that we'll be dealing with is error propagation. So, in performing measurements, there are errors that are committed. So, errors in sum or difference could be accounted by considering range of errors using the formula. So, say for example, if we have measurement number 1, so it is the measurement with consideration to error or deviation from the true value or the mean. Okay, so another measurement number 2 with the corresponding deviation or error. Okay, so how is error propagated? By adding, say for example, m1 plus m2 with corresponding errors. How do we determine? So we have m1 plus m2 in this case, this one plus this one could be obtained by adding the mean of m1 and m2 plus the quantity of this one. Okay, so these are errors attributed to, or deviations attributed to measurement 1 and deviations attributed to measurement number 2. Okay, so the plus and minus, as what you can see, implies that there are 4 possible ways of combining them. As what you can see, okay, all of this added to this, it could move up, straight, all positive. Okay, adding this, it could go down or negative. Or adding this, it could go move up and move down. Another possibility is that it can from down up. So there are 4 possible ways of combining or to deal with the what we call absolute error. Okay, so for example, we have this, okay, the values of 2 masses, for example, mass 1. So since we're dealing with mass, we'll use kilogram as the unit. So for example, your measurement is 50.1 plus or minus 0.1, and the mass of 62.1 plus or minus 0.2 kilograms. Okay, so determine the sum of 2 masses. Then to determine this, we have big letter M, combination of 2 masses. Then to obtain this capital letter M, which is the combination or the sum of these two, we just add their M1 and M2 values, 50.1 and 62.1, resulting to 112.2 kilograms. Okay, for delta M, then we have M1, we have 0.01, 0.1, and 0.2, which results to 0.3 kilograms. Okay, so to determine the percentage of error, we have the delta M, which is 0.3, divided by the M, or the sum, which is 112.2. So by performing this, and by multiplying this with 100%, we can say that the error that is committed is 27%. Then the final report could be 112.2 kilograms plus or minus 0.27%. This is the error. Okay, so that's how we report our final result. Okay, so why is this important? No? In some scientific papers, it's impossible for you to publish your work, especially internationally, if you fail to report some errors or you fail to account errors in your measurement. Okay, it's okay for high school students or for simple experiments to just simply present that without considering errors. However, if you are really into scientific work, these errors plays a very significant role. They're always considered by some scientists, especially in doing this, what we call their scientific work. Okay. So error propagation on difference. Last time we are adding, but this time we are subtracting. So of course we follow the same pattern. If we subtract 2 values having their corresponding value and their corresponding errors, then we use the same approach. Okay, so similar method. So M1 minus M2, and then we consider this one. That's how still we deal with errors in measurement, similar to how we do it in addition. Okay, next we'll deal with product or quotient. So once again, when we deal with product or quotient, so for example, we have M. So the measurement M has its value obtained plus considering the uncertainty, delta M. We have measurement N, we have this N plus the uncertainty plus or minus. Okay, so if we multiply the two, for example, M times N would result to X. Let us assume that X is the result. When we multiply M times N, the result is X. Just use X. Okay, we could expand this into an equation using your algebra. Probably, if you will recall, we can extract X leaving this equation. Okay, so we have 1, but if we distribute this, you will notice it's just the same as this one. only that we've factored it out and we've expanded it. Okay, so further expansion would lead to this equation. Okay, this equation simply tells us about the relationship of the three variables when we are dividing or subtracting. So this is the formula if we wish to consider errors as far as division or multiplication is concerned. Okay, we follow this formula. Okay, so this is the product. This is first variable. This is the second variable. Okay, so we account for errors. So for example, we have the specific one. We have the force. Force is equal to mass times acceleration. So given a force and acceleration acting on an object, determine the mass and its error limits. Okay, the mass here could be obtained by dividing force divided by acceleration. Supposing the force in our case has this value and it has corresponding error or uncertainty plus or minus, the unit is n, which stands for Newton, no? So we have it quantity. Okay, acceleration, which is also having, for example, this thing, plus or minus error in the meaning acceleration. It should be enclosed in parentheses. Okay, so that's it, no? They have corresponding uncertainty. Okay, so using the formula, F divided by A is equal to M, we can obtain M. So we can do that by simply dividing the F, which is 5.10, divided by the A, which is 2.20. Of course, the result is 2.3 kilograms. However, to account for error, so this is how we account for the error. Using the formula that we have last time, this could be our X, this could be our other variable, first variable, which is F. This could be our other variable, which is A, in this case. So we try to account for errors on the variables that we combine. Okay, so on the first error, we have 10 divided by 5.1. This is accounting the error of the first variable, this F. We have 0.1, this one, and 220. This is accounting for the error of the other variable, A. Okay, and combining this will result to 0.02. Performing this will result to 0.05. And adding the 2 will give us 0.07. So delta M over M gives us 0.07. Okay, so what is the implication of this? Okay, let's continue. So the absolute error mass could therefore be determined as delta M. Okay, there is an over M, but this time the M is transferred here. Okay, so delta M is equal to 0.07. This is the one that we obtained a while ago. Delta M over M is 0.07. In algebra, we could transfer M here to the other side. So delta M is equal to 0.07 times M. Okay, so as what we can see, it's here. Delta M is equal to 0.07 M. Okay, therefore our delta M could be obtained by multiplying that with our by considering 0.07 times the value of our M, in which the delta M obtained is 0.2. This is the absolute error mass. Okay, therefore the final report could be obtained by considering the propagation of those errors to be mass is equal to 2.3 plus or minus 0.02 kilograms. Okay, so it seems that these things are new to you, but once again, if you are serious later on and if you wish to pursue scientific careers, then this type of error consideration, it plays a very important role, especially for those who would like to pursue later on a degree in BS Physics or MA Physics or pure sciences. Then these concepts are very important. Okay, that's all for today. So probably I might be giving you some activities later on. So for example, you will be given data, you will perform similar tasks in which you will be practicing how to determine percentage of errors and all those stuff. So I hope that this video helps you, and if you have any questions later on, so you just shoot them on our stream, your Google Classroom, and I hope you have learned something, guys. It's getting tougher and tougher. However, I hope that you will enjoy physics, and just keep safe and enjoy learning. So I hope that all of you are doing fine and you can perform well on the exercises that I will be providing you later on. Okay, so credits to the following. So once again, similarly, I try to consider these references, and once again, good day, and this is the end of this presentation. So I hope to provide you with additional videos on other topics. So keep safe and God bless to all. The idea or the concept of or the meaning of the data that we have obtained. Okay, it is also possible to determine the percentage of error using the formula. So to determine the percentage of error, we simply consider the fractional error times 100%. So fractional error times 100% once again will just give us the what we call the percentage of error. In our example there, our percentage of error would be, okay, so we have fractional error times 100%. This is 0.004%. Okay, so that's the idea that we have.